Imagine you are trying to walk into your favorite local coffee shop. You're thirsty, you have your money ready, and you just want a latte. But when you get to the sidewalk, you see a crowd of 5,000 people standing in front of the door. They aren't buying coffee. They aren't even talking. They are just standing there, packed shoulder to shoulder, blocking the entrance so completely that not even a breeze can get through. You can see the baristas inside, ready to work, but they are just staring out the window in confusion because their shop is effectively cut off from the world. This is exactly what a distributed denial of service attack, or DOS, does to the internet. It doesn't use a master key to break in, and it doesn't steal your data like a thief in the night. Instead, it uses the sheer weight of numbers to suffocate a target until it can no longer function. Today, we are breaking down every major type of DDoS attack in existence, from the old-school floods to the modern, sophisticated application layer assaults that can bring down entire nations. If you've ever wondered how a website with millions of dollars in infrastructure can be silenced by a teenager with a botnet, you're about to find out. To understand a DDoS attack, we first have to understand the difference between a regular DOS and a distributed one. A standard denial of service is like one person shouting at a librarian so loudly that the librarian can't hear anyone else. It's annoying, but the librarian can just point at that one person and tell them to leave. A distributed attack is when 500 people walk into the library and all start whispering different questions at the same time. The librarian can't just kick one person out because the noise is coming from everywhere. This is the distributed part. The attack comes from thousands or even millions of different IP addresses simultaneously, making it almost impossible to tell the legitimate users apart from the attackers. The first major category we need to tackle is volumetric attacks. These are the brute force of the DDoS world. The goal here is simple: saturate the bandwidth of the target site so that no real traffic can get through. Think of it like a massive traffic jam on a highway. If an attacker can send 100 gigabits of data per second to a server that only has a 10 gigabit connection, that server is going to look like it's offline to everyone else. The most common type of volumetric attack is the UDP flood. User Datagram Protocol, or UDP, is a connectionless networking protocol. This means it doesn't require a formal handshake to start sending data. An attacker sends a massive number of UDP packets to random ports on a remote host. The host then has to check for an application listening at those ports, and when it finds none, it sends back an ICMP destination unreachable packet. This process consumes the target's resources, and when done at scale, it completely overwhelms the system. But attackers are lazy, and they don't want to use their own bandwidth to do this. This led to the rise of amplification attacks. This is one of the most clever and frustrating tactics in the book. The attacker sends a small request to a third-party server, like a DNS server or an NTP server, but they spoof the return address so that the server thinks the request came from the victim. The trick is that the response from the server is much larger than the request. For example, in a DNS amplification attack, a tiny query can trigger a massive response filled with records. By sending thousands of these tiny queries to open DNS resolvers across the internet, the attacker can multiply their traffic by a factor of 50 or even 100, aiming the resulting fire hose of data directly at the victim's IP address. It's like ordering a single pizza for a neighbor, but doing it through a system that turns that one pizza into 50 family-sized boxes delivered all at once. Then we move into the second major category, which is protocol attacks, also known as state exhaustion attacks. These don't necessarily try to overwhelm the bandwidth, but instead, they try to consume the actual processing resources of the network equipment, such as firewalls, routing engines, or the servers themselves. The most famous version of this is the SYN flood. To understand this, you have to know how computers talk via the TCP three-way handshake. Normally, computer A sends a SYN packet, computer B sends back a SYN ACK, and computer A finishes with an ACK. In a SYN flood, the attacker sends a massive number of SYN packets but never sends the final ACK. The server sits there with a half-open connection, waiting for a response that will never come. Each of these half-open connections takes up a small bit of memory in the server's connection table. Eventually, the table fills up, and the server can't accept any new, legitimate connections. The server isn't broken, it's just full of people who walked up to the counter, said hello, and then stared blankly into space. A variation of this is the ping of death. While this is an older type of attack that most modern systems are protected against, it's a classic piece of internet history. It involves sending a malformed or oversized ICMP echo request, a ping, that exceeds the maximum allowed size of 64 kilobytes. When the target computer tries to reassemble the fragmented pieces of this oversized packet, it causes a buffer overflow, which can lead to the system crashing or rebooting. It's the digital equivalent of trying to fit a gallon of water into a pint glass. The glass is going to break. While you don't see this much anymore, it paved the way for more sophisticated malformed packet attacks that target specific vulnerabilities in network drivers. Now we get into the really sneaky stuff. Application layer attacks, or Layer 7 attacks. These are the most difficult to detect and mitigate because the traffic looks almost exactly like legitimate user behavior. They don't try to flood the pipes or crash the routers. Instead, they target the very top of the stack, the applications themselves. A common example is the HTTP flood. This is simply a swarm of GET or POST requests aimed at a specific part of a website. Imagine an attacker finds a specific page on a site that requires a lot of processing power to load, maybe a complex search query, or a page that generates a large report from a database. By instructing a botnet of 10,000 computers to refresh that specific page over and over again, the attacker can max out the server's CPU and memory without using much bandwidth at all. To the network security, it just looks like the website has suddenly become very popular. A subset of this is the slow loris attack. This is a highly efficient type of attack that allows a single machine to take down a massive server. The attacker opens multiple connections to the target web server and keeps them open as long as possible. They do this by sending partial HTTP requests that never finish. Every few seconds, they send another tiny bit of information to the server to prevent the connection from timing out. Because the server has a limit on how many concurrent connections it can handle, it eventually runs out of room for real users. It's like someone walking into a restaurant, sitting down at a table, and ordering one single French fry every 20 minutes. They aren't causing a scene, they aren't being loud, but they are taking up a seat that a paying customer could be using. As the internet evolved, so did the tools used to launch these attacks. This brings us to the concept of the botnet. Most DDoS attacks today aren't launched from a single supercomputer. They are launched from thousands of zombie devices that have been infected with malware. This is the Mirai botnet model. In 2016, a piece of malware called Mirai started scanning the internet for Internet of Things or IoT devices, things like smart cameras, routers, and even refrigerators that were using their factory default usernames and passwords. It infected hundreds of thousands of these devices and turned them into a massive, coordinated army. When the owner of the botnet wants to attack a site, they send a command to the command and control server, which then tells the entire army to start flooding the target. The terrifying part of this is that the owners of these devices usually have no idea their smart camera is currently helping to take down a major bank. Why do people do this? The motives for DDoS are as varied as the attacks themselves. Some are for political reasons, known as hacktivism. Groups like Anonymous have famously used DDoS to protest against governments or corporations they disagree with. Others are for financial gain. We see this in ransom DDoS attacks, where an attacker sends a sample attack to a company's website and then sends an email demanding a payment in Bitcoin to stop the next, much larger attack. It's a digital protection racket. Then, you have the diversion attacks. This is when a small DDoS attack is used to distract an IT team. While everyone is scrambling to get the website back online, the hackers are quietly sneaking into a different part of the network to steal sensitive data. It's the smoke bomb of the cybercrime world. We also have to talk about the Smurf attack. This is another older method that uses ICMP packets. The attacker sends a ping to a network's broadcast address, but spoofs the source IP to be the victim. Every single computer on that network then dutifully sends an echo reply to the victim's address at the same time. This turns one packet into hundreds, flooding the victim with replies they never asked for. This is why most modern networks are configured to ignore broadcast pings, but in the early days of the web, it was a devastatingly simple way to knock someone offline. As defense mechanisms like Cloudflare and Akamai became common, attackers had to get even more creative. This led to multi-vector attacks. Instead of just picking one method, an attacker will launch a UDP flood, a SYN flood, and an HTTP flood all at the same time. This forces the defense systems to fight on multiple fronts. If the security team manages to filter out the volumetric flood, the application layer attack might still get through. This constant cat and mouse game is why DDoS protection is now a multi-billion-dollar industry. You can't just have a static firewall anymore. You need intelligent systems that can analyze traffic patterns in real time and distinguish human behavior from machine-generated swarms. Another sophisticated move is the pulse wave attack. Traditional DDoS attacks usually look like a big spike that stays high for hours. A pulse wave attack is different. It hits the target with a massive burst of traffic every 10 minutes, but only for a few seconds. These bursts are so intense that they can completely overwhelm the network's mitigation hardware. By the time the security system recognizes the attack and starts to spin up its defenses, the pulse is over. This prevents the defense from ever getting a clean look at the attack pattern, and the repeated bursts can cause the network equipment to repeatedly fail over or reboot, creating a stuttering, unreliable connection for users that is incredibly frustrating to fix. Let's look at the concept of reflected attacks. We touched on this with DNS amplification, but it can happen with almost any protocol. Memcached reflection is a particularly dangerous one. In 2018, a massive vulnerability was found in memcached servers, systems designed to speed up websites by caching data in memory. These servers were not intended to be exposed to the public internet, but thousands of them were. An attacker could send a tiny 15-byte request to one of these servers and get a response that was 10,000 times larger. This allowed for the largest DDoS attacks in history, reaching peaks of over 1.7 terabits per second. This is an unfathomable amount of data, enough to saturate the pipes of even the largest global service providers. How do we fight this? It's not about just blocking IPs because there are too many of them. Instead, we use techniques like scrubbing centers. When a massive attack hits, the victim's traffic is redirected to a high-capacity network owned by a DDoS protection company. These centers act like a massive filter. They receive the dirty traffic, use advanced algorithms to strip away the malicious packets, and then send the clean traffic back to the original server. It's like taking a bucket of muddy water and running it through a high-tech filter until only the clear water remains. This allows the website to stay online even while it's under a massive assault. Then there is black hole routing. This is the nuclear option. If a DDoS attack is so large that it's threatening the stability of an entire service provider's network, the provider will simply black hole all traffic destined for the victim's IP address. This means they just discard every packet, whether it's malicious or legitimate. This effectively takes the victim offline, but it saves the rest of the provider's customers from being collateral damage. It's the ultimate victory for the attacker. They achieved their goal of silencing the target, but it's often the only way to protect the pipes that the rest of the internet relies on. We also have to discuss the human impact of these attacks. We often think of it as a technical problem, but it's really about disrupting lives. Think of a DDoS attack on a hospital's patient portal, which prevents doctors from seeing records, or an attack on a flight scheduling system during the holidays, or even just a small business that relies on its website for its livelihood. A single day of downtime can be a financial disaster. Psychological stress on IT teams is also immense. They have to work through the night, staring at monitors, trying to find a needle in a haystack while their bosses and customers are demanding answers. The silence that a DDoS attack creates is a form of digital isolation that can be incredibly damaging. The rise of DDoS for hire services, also known as booters or stressors, has made these attacks accessible to almost anyone. For as little as $5 or $10, an individual can rent time on a botnet to knock a rival out of an online video game or take revenge on a small website. While many of these services hide behind the excuse of being testing tools for network administrators, everyone knows their true purpose. Law enforcement agencies around the world, like the FBI and Europol, have been cracking down on these sites, seizing their domains and arresting their operators, but new ones pop up as fast as the old ones are closed. As we look toward the future, the Internet of Things continues to be the biggest security hole. Every time someone buys a cheap, smart light bulb or a discounted webcam that lacks basic security features, the global botnet gets a little bit stronger. We also have the threat of AI-driven DDoS attacks. Imagine an attack that can automatically change its own packets to mimic the exact version of the browser that a legitimate user is running, or an attack that can learn to bypass a specific firewall's rules in real time. This smart traffic will be even harder to filter out, leading to a new era of intelligent defense systems. Another emerging threat is the vertical DDoS. Instead of targeting a website, attackers target the hidden infrastructure that the internet relies on, like the BGP routing system or the root DNS servers. A successful attack on one of these could potentially knock out entire regions of the world, because these core systems are designed for trust and speed rather than defense against swarms. They are particularly vulnerable if an attacker can generate enough volume. We also have to mention the concept of the application-specific attack. This is when an attacker doesn't flood the web server, but instead floods a specific API or a payment gateway. For example, by flooding the login function of an app, the attacker can prevent anyone from signing in, even if the rest of the app is working perfectly. These targeted strikes require more knowledge of how the victim's software works, but are much more efficient than just noise attacks. So, what can the average person do? While most DDoS protection happens at the server level, being a good digital citizen helps. This means keeping your home router updated, using strong passwords on your IoT devices, and not clicking on suspicious links that could turn your own computer into a zombie in an attacker's army. If you own a small business website, using a content delivery network or a basic DDoS protection service is no longer optional. It's a necessity. The history of DDoS is a history of the internet's growing pains. It started as a way for hackers to flex their technical muscles and evolved into a serious tool for crime, protest, and even warfare. It exploits the very thing that makes the internet great: its openness and its best effort delivery model. Because the internet wasn't built with armored pipes, we have had to build the armor ourselves after the fact. Every time a major attack happens, whether it's the assault on Dyn that knocked out most of the US East Coast or the record-breaking floods against Google, we learn something new. We build better filters, stronger networks, and more resilient systems. The battle against DDoS is a war of attrition. It's about making the cost of the attack higher than the reward. By using distributed defenses, scrubbing centers, and intelligent traffic analysis, we make it harder for the bad guys to win. But as long as there is an incentive to silence someone online, the attacks will continue. It's a permanent part of the digital landscape. But by understanding the every type of DDoS, we take away the mystery. It's not magic, it's just math and volume. And once you understand the math, you can figure out how to solve the problem. Imagine that coffee shop again. If the baristas had a way to instantly identify the fake customers and politely move them to a different, invisible street, the real customers could walk right in. This is exactly what modern DDoS protection does. It's an invisible, silent struggle happening millions of times every day, ensuring that the websites and services we rely on are actually there when we need them. It is the silent guardrail of the internet. As we integrate more of our lives into the cloud, the stability of these connections becomes even more vital. We are moving toward a world where a car's navigation, a city's power grid, and even our own health monitors are all online. Protecting these systems from being flooded is not just a technical challenge, it's a safety requirement for the 21st century. DDoS is a dark reminder of the power of the many and the importance of protecting the one. Think about the sheer scale of the data we're talking about. Terabits per second. Millions of packets every heartbeat. The fact that the internet works at all while under this kind of constant, high-pressure assault is a testament to the engineering that keeps it running. Every time you load a web page smoothly, you're potentially benefiting from a massive, multi-layered defensive system that just filtered out 1 billion malicious requests specifically designed to stop you from seeing that page. The story of the DDoS attack is a story about the fight for the available internet. It's a fight that never stops, evolving from simple pings to complex, AI-managed floods. But for every attacker trying to block the door, there are thousands of engineers, security experts, and ethical hackers working to keep it wide open. It's a battle of minds, scripts, and bandwidth, and it's one of the most fascinating aspects of our digital age. By staying informed about how these attacks work, you're not just learning about computers, you're learning about the fundamental mechanics of the modern world. Stay curious, stay vigilant, and always keep your digital doors well guarded. The internet is a massive, crowded library, and as long as there are people trying to whisper everyone into silence, there will be someone there to make sure the real voices are still heard. The next time your favorite site is slow or returns an error, take a second to wonder, is it a server upgrade or is it a battle? Most of the time, the battle is invisible, but its results are what allow us to keep exploring, communicating, and building in the digital space. The library is still open, the quiet voices are still being filtered out, and the librarian is getting better at their job every single day. That is the true state of the available internet. Constant defense, constant evolution, and a constant commitment to keeping the lanes of information clear for everyone. Until next time, keep exploring the vast world of technology, but always keep an eye on the defensive lines that keep us all connected. The world is a big place, but the internet makes it smaller, as long as we keep the traffic moving.